Okay, good. My name is Mikhail. I'm especially happy to give this talk at a conference which is dedicated to serverless, so I don't have to explain what serverless is, what the benefits are. I can spend all my precious time on the thing that I care most is performance, and comparing the performance characteristics of different FaaS providers. So in the past, we used to run our applications on servers. They are very nice and cozy. We were defining the specs of those servers. We were installing software. We were taking care of them. We could SSH to them. We could profile them. We could have performance under the control, or at least we had a feeling that we had it under control. That kind of changes when we move to the cloud, and especially to serverless. You don't know anymore where your application runs and on what kind of CPU is being used. So instead of control, you kind of have to trust the cloud provider to do the best job possible. And in my opinion, the best trust is informed trust, when you know what's going on there behind the scenes, not just blindly believing that it will make your application auto-scale magically and always work. So that's the point of my session today. And the way I'm going to attack this is twofold. I'm going to tell you a story of my own about the project that I did and how I ended up looking into performance characteristics of different cloud providers. But also, I did a number of experiments which are generic and the results of those can be used by you, hopefully. So they are applicable to different projects. My own story has something to do with the World Cup that we had in Russia. I currently live in the Netherlands, but I originally come from St. Petersburg, Russia. And I obviously have still connections there. About half a year before the World Cup started, I got a call from my friend. He asked me whether I can help him to deploy an application for the World Cup. The idea is basically that a lot of people are coming to Russia. They have no idea what they're going to do there except for football and beer. They are all lost. They don't know how to use public transport or don't know what they can do otherwise. Lots of Russians don't speak English, so it's kind of hard to navigate there. So the application was aimed to help them and guide them through public transport or find some points of interest or simple things like how to exchange your currency. And apparently there was a state-run fund in Russia which was giving money to projects related to World Cup. And my friend was a good businessman. He knew somebody who knows somebody. So he could get some funding, and he could get several months of downtime and work on this application, and also could hire a couple more people. So the idea, as I explained, is very simple. You, as a foreigner, come to Russia. You say, I'm going to this football match. I live in this hotel and have this much time. And then the application would kind of suggest you what else you can do and how to get from A to B and to get what you basically need. On a high level, the application looks like this. So you have a mobile app and also a web app done with something like React. On the back end, we used third-party services because, of course, we couldn't do navigation and transport system on ourselves. And there was this thin layer in between of a HTTP web API. Mobile app talks to this API, and what it does basically, it redirects queries to third parties, combine them in a smart way, and returns JSON back. That's all it needs. So that's the biggest square on my slide, but actually for my friend, it was the least important part. He just wanted to get out of the way and just work and never care about it, because he cared about the user experience on mobile app. He cared about what kind of results they get from third parties. But this is kind of dumb middleware. It should just work. And if we go from there and we look at non-functional requirements, he didn't want to care about servers or installing any software anywhere. Ideally, just write code and put it somewhere to run. Performance and scalability were kind of interesting because nobody will use it before World Cup. During the World Cup, we didn't know how many people might pick it up. Maybe nobody, maybe 1 million people, we don't know. So ideally, it would work for everyone. And of course, price-wise, if nobody is using it, ideally we shouldn't pay anything. And if people are using it, we'll probably make some profit, so it's fine to pay a fee. That's a very reasonable model. And as you might guess that a really good match for function as a service, serverless platforms. I come from Microsoft background, so I suggested using Azure Functions as the first candidate. He was running a previous version of this application. He had a basic already in something called Google App Engine, so he was pretty happy with Google. And also he heard that AWS is a market leader. So we kind of had a debate about this, and then we decided, all right, let's just do all three of them and then compare, because why not? They're all kind of similar. They all run JavaScript at least. Google runs only JavaScript, or at least in production. But they all support JavaScript. We use something called Serverless Framework on top of that, so it kind of abstracts a bit the differences between cloud providers. And then we had a small layer of our own code. It appeared to be pretty simple to put the same application just doing the request to third parties on all three providers. So that's how the same setup works. We have Lambda, Azure Functions, and Google Cloud Functions in between, serving RESTful API for mobile app and web app, and then calling HTTP services on the backend. Pretty simple. For each arrow here, we also made some sort of handmade instrumentation, so we recorded all the requests and how long they took. And also we recorded the dependencies that we called and how long they took, so we could compare and kind of be in control of whether we are meeting the performance requirements. When I talk performance, I basically mean two things. One is throughput. They mentioned users, basically. How many requests we can serve per second. We can scale, whether we can scale from 1 user to 1,000 to 1,000,000. And then the second one is latency or response time. So while we are growing from 1 user to 1,000,000, are we able to keep the response time under control? Ideally, it should be flat, but it can grow a little bit, but not too much. So that's what I'm going to talk about for the rest of the talk. I have several parts. They all start with a yellow screen. We came up with a very basic version of application and started running them on all three cloud providers. Obviously, no real users yet. We were testing it ourselves, and a couple of friends helped us. So a typical usage pattern looked like this. In 5 hours, maybe not even typical, but the most busy hour of the application. In 5 hours, we get like 20 users, and they did something, and then they quit. So very quiet, no real scalability issues should be at this point. Ideal point to start measuring stuff. First, we measured the dependencies, whether they are fast. This chart shows like response time for several requests. They are all around 100 milliseconds, 150 milliseconds, which is pretty good. We are calling a service in a different geographic location, so it's quite fast. And then we said we want to be a little bit above that, not too much. Like if we are 200, 300 milliseconds, that's fine. That's very fast on your mobile app. So we want to be this fast. And we started measuring. We measured on Lambda, the yellow points on these charts. You can see that they are above our target, or actually there are two groups. One group is low, one group is high. It's still 500 milliseconds, not a big deal, but still getting weird. We looked at Google Cloud, and that's even more out of control, so it's now 2,000 milliseconds or 2 seconds, or even more sometimes. And the same picture of 2 rows on the chart, right? Azure, the same thing, 2 groups, now going up to 4 seconds, and one group is very fast. So what's going on here? You probably can guess that the thing that's going on here is called cold start. Basically, when you deploy your serverless application to any of those cloud providers, you just put a zip file with the code. And then when they get the first request, they need to find a VM. They download your code. They start the runtime like Node.js or .NET or JVM. And then they run your code, load your dependencies, and then they are ready to serve your first request. And that, of course, takes time. They are not stupid enough to actually boot a new VM for this request. They have like a generic pool of workers ready for any customer to serve, but still the customization has to happen on this request. Then the next request comes. They are smart enough to reuse this VM for some period of time. So the next request comes in. They can immediately serve this request from the existing VM. And that's a warm start. And that's the fast points on my chart. So if we get back to this usage chart, those periods of inactivity in between, they probably triggered cold starts every time. Because after some time, cloud provider decides, okay, nobody's using it anymore. Let's recycle it again. And the cold start will happen again on the next request. So it's not just the very first request. It's every request after inactivity time. What's this inactivity time? We have the data. I ran this experiment last time in August, so pretty relevant. On Azure, this chart is different. On a horizontal scale, it's showing time between two requests, so how long of idle time we had. And then vertical axis is how long it took to serve the request. And you can see pretty clearly that 20 minutes is the threshold. At 20 minutes, they kill your instance if it's idle, and then they'll start a new one if that needs to happen. On Google, it's completely different. It's almost random, I would say. They can kill your instance after 3 minutes. They can leave it more than an hour. As far as I understand, they do this based on demand supply. So if they have a lot of generic instances in the pool, they allow your instance to live longer. If they kind of have shortage of those, they will run garbage collection of everyone's instances and then put those into the pool. Amazon is kind of in between. They keep your instance for almost half an hour, although in official documents I think they still say just 5 minutes, but they do longer. And then it starts to grow over time. The longer it takes, the more probabilities it's going to be killed. So I think that's the point where all cloud providers will probably come at some point, because it's a reasonable compromise. The goal of the cloud provider is to, of course, minimize the infrastructure they use, so they want to save and kill your instance as fast as possible, probably, if they think it's idle. But the goal of customer, of course, is to keep it forever. So it's a bit clashing, and then it's the call of cloud provider to determine exactly where this should happen to keep customer happy, but also keep the cost down. As to how much the cost is, that's might differ per cloud provider and per supported language. On this chart, I have all GA languages. You can see that it's between 0.2 seconds and 4 seconds. And that's just Hello World application, right? That's just 5 lines of JavaScript that you deploy, or the very basic C# function. You also see that AWS is probably doing a better job now. Google is a bit faster than Azure, and somehow .NET is the slowest language of all supported on AWS. But that's just Hello World. If you start adding dependencies to your application, of course, that will add up. If you need to load NPM modules, they grow very fast, or NuGet packages, or Maven packages, whatever you are using. So I ran this experiment where I deployed 2 applications, one with 5 megabytes of NPM packages zipped, the other one with 35. And you see that the blue or the darker squares, they show the penalty that you pay for this compared to Hello World. Again, AWS is faster, Azure is slower, might change over time. They're all aware of this problem, and they are working on minimizing this. So can we actually fight a cold start? There are workarounds. It's easiest to do on Azure, because for every function app, basically a unit of scale, you can have multiple functions, and you can make one warmer function, which is triggered every 15 minutes, doesn't do anything, but just keeps your instance alive. Kind of hacky. Defeats the purpose a little bit, but you don't end up paying for it. It's just 100 milliseconds every 20 minutes. But it feels kind of wrong. For Lambda or Google, it's more complicated, because you would have to create a separate warmer function triggered by CloudWatch, for example, and then that function should invoke your target function. The target function should understand that that's a warmer request, not a real request, and quit immediately. So it gets hairy pretty fast. There are NPM packages, blog posts around that. It kind of works, but I hope they will fix it themselves at some point. Another problem with those approaches is that you don't get 100% reduce of cold starts. They will still kill your instance after several hours or several days, depending on provider. And also, whenever you need to scale out, so go from 1 instance to 2 or from 5 to 6, that extra instance will hit cold start again. And that's practically impossible to fight if your traffic has jumps in usage. So the first lesson to know, be aware of cold starts. They are slowish, depending on your requirements. Try to keep your functions lean as possible. Don't do too many dependencies. And if your scenario is somewhat real-time-ish, then that might not be the best choice at the moment. Second scenario, okay, we understood the cold starts. Now we decided to load test our application to understand where we stand under the load. For this, we rolled out our own tool. Of course, we are developers. I'll explain it briefly. So we have our application under test, again in all 3 cloud providers. We run yet another serverless function next to it, which is a caller function. It can call the target function, for example, 100 times, and record all the response times into the database. Then, in the beginning of pipeline, we have like a scheduler or manager or whatever, who sends messages to the queue saying, please send 100 more requests, please send 100 more requests, and so on. And this way, we can really model the shape of the load that we want to get, like over time, growing or pretty linear or like spiky or whatever. That works very well. Because caller makes multiple invocation in one call, it doesn't have to scale it to the same amount of instances as the HTTP function, so it's not a problem on that part. If you don't want to do this yourself, I think it took like several hours, but still, and you are an AWS, there is a tool which will do this for you. It's called Serverless Artillery, done by Nordstrom. It's basically doing the same thing, but just for you already implemented. You define a scenario. In this example, it's a basic constant level of request, but you can define some JSON or whatnot for your scenario. And then it will try to hammer your application as fast as possible, or according to scenario. And the application under test doesn't have to be serverless. You can basically load test any HTTP endpoint that you want to do, or try to DDoS somebody. That's a scenario that we came up with initially. We said that in our happy world, when everybody will use our application, we'll get like between 10 and 20 requests per second. I think it's just guessing, but we have to start with something. So we ran this workload for 5 hours again, and we recorded the response time. It was mostly okay, but one function was kind of sluggish. It was growing to seconds again, second, 2 seconds, 3 seconds, sometimes even failing. The reason we understood immediately when we plotted duration of third-party calls on the same chart. Basically, all the time that we were just waiting for a web service to return us the result. It appeared that we were violating their SLA. We were only allowed to call it once per second or so, and we were doing more frequently. And they probably were throttling us or just had troubles to keep up themselves. So that was a problem for us. An intermediate lesson here is that with serverless application, it's quite easy to DDoS anything else that you have on your stack. Like if you have a legacy web service or a third party or SQL database for that matter, it's it's easy to scale your serverless application, but it's not easy to scale that thing. So there are scenarios where you actually don't want to scale your serverless application and to limit it. Especially that's true for asynchronous scenarios. When you have a queue, you are not very keen on making it as fast as possible, but you are keen not to overload the rest of your system. And then there are tools to limit the scalability of your serverless application to the level that you want. For example, if you are using Kinesis or Event Hubs, I'm not sure if Google has something like that, you can define partitions, and then your Lambda or Azure function will not scale beyond that partition. So if you have 4 partitions, it will only run up to 4 instances at the same time. So that's a natural way to scale, to limit the maximum concurrency. If you are not on Kinesis, or for example, you're using SQS or Azure Queues or Google PubSub, that will not work. But there are some settings in AWS. It's confusingly called reserved capacity, but I read it as maximum capacity because that's what it is. So if you say it's 10 for this Lambda, it will never scale to 11. It will just keep it up to 10. In Azure, there is a similar setting which only works for values below 5 at the moment, but they will probably fix it at some point. On Google, I don't know. I didn't find any. The lesson here is, if you look at the architecture of your application, you should consider that the overall scalability is limited by non-serverless dependencies, non-serverless parts, as was the case in our example. So we had to work around this problem, and that means we had to change our application. Instead of that nice and cozy diagram that I had before, we changed it to be something like this, or at least for that critical path. We started using database of the cloud providers, so DynamoDB, Cosmos DB, and Google Data Store, what's the name? Basically key value. And then we would preload data from third-party provider into this database in advance. And then instead of hitting them on hot path, we would hit them on cold path asynchronously and load the data from there. We were lucky that this was possible for this service. Basically what they do, they just dump their data once a day, once a week, and then we could parse that file and then send a lot of messages into the queue, and then have a function, which I called Serverless Glue here. It's not AWS Glue, confusingly. It's just another Lambda, which is triggered from the queue, and then it saves data to the database, pre-processing it and making the right format for us and so on. Frankly speaking, we didn't really care if it will take an hour or a minute to process this batch, because it's relatively slow changing information. And I did not do good measurements on that time. So while preparing this talk 2 weeks ago, I made several runs of how serverless functions scale under large batches of queue messages. So I was throwing like 100,000 messages into the queue, and then measuring how much it takes to process them and what the scalability looks like. I think that's quite curious. I'll spend several minutes on that. But first I need to explain how actually the providers scale their applications a little bit. Well, not in depth, but a sketch of it. It differs. For AWS, we have a SQS trigger, and they have what they call concurrent executions. So at any given moment in time, they might run n instances of your Lambda. And each instance gets just one message. It cannot do multiple at the same time. Even if you called a third party and now we are waiting for 5 seconds, it just stands idle. You pay for this. But it doesn't run multiple at the same time. And it doesn't know about SQS. It just gets the message from somebody. This somebody exists in AWS. I don't think there is an official name for this party, magical thing. I call it orchestrator in this diagram. That's the thing which connects to SQS, gets batches of messages, and then decides how many concurrent executions it needs, provisions those, and sends one by one to those executions, saying, you do this, you do this, you do this, you do this. Okay? So it's quite a complicated thing. It's not publicly described anywhere, to my knowledge, but it has some characteristics. Again, in ideal world for us, consumers, they would just spin up 100,000 instances, give one message to each, but that's super inefficient. You remember cold starts, and then they'll have to, again, garbage collect them, distribute to another customer. So that's very resource consuming. In ideal world of cloud, probably they would just have one instance processing message one by one. Very effective, but not fast enough. So again, they try to find a compromise which satisfies everybody. And in case of SQS, they are quite explicit about explaining how. They say that they will add 60 concurrent executions every minute of your backlog. Every minute you get 60 more. Next minute, 60 more, 60 more. So when I ran 100,000 messages into SQS queue, and the function was basically just waiting for half a second, effectively. So it's sort of I/O bound. It's not, it doesn't have hard requirements to CPU. It doesn't do any expensive stuff there. So the chart looked like this. The yellow line goes down. That's the backlog of the queue. And then the instances grow pretty much linearly. They keep the promise. They add 60 per minute. So by the minute 5, we have 300 something. That looks pretty decent and quite predictable. The second function of mine was CPU bound. So it was calculating, brute forcing some passwords. Very CPU demanding. But it's actually the same picture. Well, it's a different picture. It took 10 minutes now instead of 5, but that's because one execution just took longer. And they keep this promise. Now we got to 600 instances. I think 1,000 is a hard limit where they will stop. But it's still, they still keep the promise. Another variable that you have there is that you can control amount of provisioned memory for your Lambda. And it's not only memory, but you also give CPU proportionate to this memory. So this function was doing 128 megabytes, the smallest possible instance in AWS. It also got just a little bit, a tiny fraction of CPU, of actual physical CPU on the server. If you provision 4 times more memory, you get 4 times more CPU at the same physical time. So if you run it on 512 megs, it will complete 2 times faster. 2 times because that's quadratic, not 4 times. But the instance growth is the same. It's perfect. I didn't show it here, but it's the same formula, 60 per minute. That's for Lambda. To my best guess, Google Cloud Functions just took everything, like the model itself from AWS. They have exactly the same kind of concurrent executions and one per instance and so on. But they have different characteristics of that orchestrator because they are finding different balance. Same task executed on Google Cloud looked like this. So somewhere at the first minute, they just jumped to 300 instances immediately. And so they were faster to reach the point of 0. After that, they refused to grow for 5 minutes. But on CPU workload, it looked different. They were jumping like every minute more and more instances and were done again much faster than AWS. When was the last time that you ran your application on 1,200 instances? It's just several lines of JavaScript and then deploy it to Google, and it just works. Google has the same model of memory CPU allocation, but surprisingly, when I ran it on bigger memory, it got slower. And the CPU got faster, but actually they refused to scale that fast. They were just scaling much slower. Again, I assume it's the same supply-demand model. It's much easier to find a small instance somewhere on a server, or 1,000 of them, than to find 2 gigabytes of instance and full CPU available. So I guess they are kind of trading your scaling for their own benefit. It might change over time, but they don't document any of that, and so it's just, this chart is your best hope to understand how it works. I assume it will change over time, so if I run it again and again, it might be different every time. But I didn't do this. Now for Azure, the model is quite different. If I try to draw the same picture for Azure, the queue is now called storage queue, which is not important. But the unit of scale is called function instance, and the function instance is more powerful. It talks to the queue itself without intermediate parties, gets the batches of messages, and then executes the whole batch in parallel on the same instance. So it runs multiple handlers at the same time on one instance. That's beneficial if you do like IO-bound workload. If you call a database or a web service, they can keep using resources while one request is idle. But they still need to scale it, so they have a thing called scale controller. It sits somewhat on the side, it monitors everything, and then it makes decision how many instances it needs, based on its own judgment. I can imagine it's a bit harder to do so, because you need to guess what the behaviors of instances are without really controlling them. So on the same benchmark of IO-intensive workload, they did about the same time as AWS and Google, 5 minutes-ish, a bit faster than AWS. But look at the number of instances, it's just 20-something, so it's much more, it packs much more requests in the same instance and also doesn't scale that crazy fast. That's upside for I/O because you also end up paying less, I believe. But that's a downside for CPU. When I run a CPU benchmark, it couldn't really keep up as fast as the other providers. It only scaled to 50-something instances. And because each message competes for the same CPU, they kind of get on the way of their own. And it took 20-something minutes for the same job. I hope you are still with me. The conclusion here is that serverless is no magic. You need to learn at least the basic resource model, learn about CPU and RAM allocation, which might not be very intuitive. Do some experiments about scaling, or at least read the document, what's the official statement on that is. Learn your cloud provider. And don't expect like sub-minute time to digest all the backlogs that you might have in the queue. It still takes minutes, in my experience. Next part, the fun one. Back to our project in Russia. Somewhere in May, my friend called me again and said, we are going to be on TV. Apparently, there is a show before the football matches, and then they said they can like demo our application there and say, hey, everybody use it there. And what that means is that a lot of people will watch this, presumably on TV, and then they get their mobile phones, install application, or go to website, use it for 5 minutes and never use it again, probably. But you get a lot of requests in a short period of time. If you are a blogger, maybe you know the term Hacker News effect, which is sort of the same for the web. When your post gets to Hacker News top, and then tens of thousands of people come to there, and your site is down. So that's what we decided to try to avoid, and otherwise, why go on TV? So that's the scenario we came up with. The first part is the normal load that we tested last time, like the first several minutes. And then it bursts to, again, arbitrary number of about 1,000 requests per second. I checked, it's like half of the load of Stack Overflow, which is not Facebook or Google, but still reasonable, right? And with our great tool, we were able to simulate this amount of requests coming to our applications, and we did that. The first time we ran it on Google, it didn't look nice. We got a lot of errors. Basically, a Hacker News effect worked. The errors were like out of quota 529 or something. But after Googling it for 5 minutes, we found the docs on Google which say that we should do this. Basically, our function was calling HTTP through HTTP, another function, and then it was killing the connection every time. We did not reuse the connections between requests. And there is a quota in Google. You can only do this much of connections per second or per minute. And then they start throttling you. Just by adding to these two lines, it fixes the problem because it will persist connections between requests on the same instance. And that's like a very typical mistake people do. They think serverless is stateless, but it's not. It's not completely stateless. You should keep like database connection pools, HTTP pools, cache may be something important. This nice article from Troy Hunt, I guess you know Troy Hunt. He did the same thing on Azure. He was opening connections again and again and then got out of quota. And the trick he did, it's a C# if you don't know, basically make a HTTP client static. And then because all your requests on the instance are running, are using the same client, they will reuse the connection pool. Database connection pooling is actually very easy on Azure again because you are running multiple things on the same instance, so you can reuse common pool. You just use the normal classes that you are used in C#, and then they will take care of reusing database connection. With Lambda, it's quite more difficult, as I understand, for SQL. There is a blog post by Jeremy Daly, and it's quite advanced. A lot of things they have to do to properly handle connection pooling and like retries, and don't be too aggressive. Be kind to MySQL in order to not to kill it. He even made an NPM library, a full library for doing this. So if you're in this scenario, go check it out. But that's a common problem. Lesson here, stateless, true, but not for everything. Keep your connections, keep your cache. It will help you handle the spikes. We fixed this. We ran it again. This time it was all 200 OK. This chart is showing percentiles. If you don't know what percentile is, like 90th percentile means that the fastest 90% of your requests were faster than this, and the slowest 10% were slower than this. So for the Google, this looked like this. You see the spike. It's not very nice. It's 10 seconds for 1% of users and 2 seconds for 5%. But it's kind of okay-ish. Maybe you're fine to annoy 1% of your users on this peak. On Azure, it looked even better. It was very smooth up until 95, so still 300 milliseconds, very fast. 99 kind of goes up. You can see the exact shape of our load. It grows and goes down again, but it's still below 2 seconds, so it's very good. Right. On AWS, it's just flat. They just didn't feel anything. They just, I don't care. 800 per second? Wow. Right? I think that's pretty amazing. I was quite surprised to see this because I don't know how to do this with any other technology that I ever used. How to scale to that many instances, that many requests go into the same web API. The lesson here is serverless is cool. It's suitable for your spiky loads, but still there are some limits and some tricks that you need to know to make it really scalable. Final part, running in production, so the World Cup. I'd love to say that we were super popular and we got 1 million users. Unfortunately not. We ended up running on AWS with Lambda. In total, we got like 4 million executions, which is really not much. We were not on TV, unfortunately. That didn't work out. On AWS side, there were no issues. We didn't notice anything. It was just working for that month or so. We had a lot of issues on mobile and third parties, but that's a different story. The total bill was like $150. I think we could optimize it further, but that's just a couple hours of work, right? So, I mean, developer time-wise. And Lambda was less than $5, so that's pretty good budget. My friend was happy. To wrap up this session, is serverless good for your project? What are my opinions? And I would say that throughput is probably good enough for 99% of your applications. If you are super critical to latency, be aware of cold starts and test how your application behaves on that. I used to say that there is no SLA for those services, but now they all introduced an SLA about uptime. I think it's still not great, like 99.9 or 99.5. Doesn't matter. But they don't give any guarantees about performance. So they don't say, they have docs which say their current behavior is, but there is no SLA for that. So if you have SLA to your customers, maybe that's a concern for you. And of course, pay attention to all the other sessions in this conference about tooling, architecture, pricing. There are pitfalls there as well. The best scenario is to start with FaaS, I would say. I use it for all the prototypes that I do. It's very easy to start and just have something working in no time. The cloud glue that I called, connecting queues and services. If you're already in the cloud using like AWS, a lot of services AWS, or if you are in Azure, connecting them together with lambdas and functions, that's really easy. For low traffic apps, apart from cold start, you will not end up paying anything, so it's a great usage. And the unusual or unpredictable load profiles like we had, that's also a great scenario. With this, thank you.